Lecture 19 is our third lecture on modern theory of solids. So in this lecture, we talk about effective mass and the concept of holes and the density of states. So first, students should be able to determine the effective mass of electrons in a band and then describe what a hole is and its characteristics. So in materials, we have a lot of electrons, but because of the crystal potential, the electrons are no longer free. So as we are treating these electrons as particles, obviously they have a mass, but the mass will be different from the mass of a free electron. So we call them effective mass. This effective mass is really treating the crystal potential as part of the environment that may drag on to the electrons and behaves as if the electron have different moment of inertia. So how do we calculate the effective mass? Well, you have to look at the band structure. The band structure basically presents all these information about the crystal potential. So if you look at the, for example, near the band edges, for let's say a valence conduction band or a valence band, these band edges, then you can apply the quadratic approximation near the band edges. You have the potential energy and the kinetic energy. And obviously for free electrons, this mass will just be the free electron mass. And this is a Taylor expansion to a second order. The first order goes away because we're talking about the extremes in the EK diagram. So in that case, this m star is really the effective mass, and then obviously it's related to a second order derivative of the energy as a function of K. So this is the equation that you can use to calculate the effective mass, and it's really related to the curvature of the EK plot. So for upward pointed band, like we have in a conduction band, this effective mass is positive. But for a downward pointed band, the effective mass will be negative. So that presents a challenge for us to look at the particles in this range. It's kind of different from classical physics. So in this case, we can introduce the concept of holes. So instead of looking at all the electrons that we have in a valence band, now let's focus on a few states that are not occupied by electrons. For those states, if we have electrons, the effective mass will be negative. But now, since we don't have electrons in those states, now we can introduce basically treat that as a vacancy or call a hole. In that case, we can assign a positive charge and a positive effective mass to those charges, and we call those charges holes. And so by looking at a small amount of holes near the top of the valence band, we can obtain all the essential information of all electrons in the valence band. The next student learning outcome is about the density of states. So you should be able to calculate the density of states of free electron gases. And first of all, the definition of the density of states, it's similar to the mass density. But now we're looking at the number of states. So if you are looking at the density of states multiplied by a certain energy interval, that gives you a total number of states with energy in between this energy interval. And sometimes people normalize that to the volume of the sample. And if you integrate all those states with energy up to a certain level, then you have the so-called total number of states. So mathematically, you see that this lowercase g, the density of states, is just a energy first order derivative of the total number of states with respect to energy. And then the total states is basically integration of all the states with energy up to a certain level. So in the case of free electron gas, we can apply the particles in the box approximation, basically use standing waves to look at the electronic states. So in that case, kx, the wave vectors component along the three dimensions are going to be quantized. There's pi over L multiplied by certain positive integers. And the energy, obviously, now can also be written in this form as it's a free electron. So in that case, if you look at the energy states in the N1, N2, N3 plot, basically Kx, Ky, Kz space. You will see that all these states are basically, for each of those quantum states with different quantum numbers, N1, N2, N3, they're going to be represented by a little box with a volume of 1. So if we want to figure out how many states we have energy up to a certain level, we only need to figure out how many of those quantum states, how many of those combinations of n's we can have within that energy. And the energy obviously is related to the sum of the squares of those quantum numbers. Okay, so with that, you can look at the total number of states, which is given by the volume of that little sphere, but understand that since all the quantum numbers are positive, we can only take on 1/8 of the volume, and this 2 is just the spin statistics, the spin degeneracy a positive spin up, spin down states. So you get the total number of states, and if you do the derivative on energy, you can get to the density of states. And the important thing that you learn here is that the density of states scale with the mass to the power of 3/2, and also it scales with energy to the power of 1/2. This is for 3D electron systems, and you can do the same thing for the 2D and 1D cases. And actually for the 2D case, the density of states goes with e to the power 0, which means it's energy independent. And for the 1D case, it goes by energy to the minus 1/2 dependent power. So the last student learning outcome is to describe the qualitative energy dependence of the density of states in the band and the quantitative energy dependence of dense states near band edges. So for density of states in the band, we have this free electron density of states, which goes by e to the 1/2. But obviously, when we go to a specific band, the distribution of the states in the energy scale will be different. But at the band edges, we can use the free electron-like approximation. As we have seen earlier, the energy goes by k², so it's kind of like free electron, but the mass will be different. So in that case, the density of states still go by with e to the 1/2. It's just that the mass is no longer the free electron mass, but it'll be the effective mass of whatever electrons you have in that system. And then when you go toward into the middle of the band, that's when you have the highest combination of different states with similar energies. As you go further away, then you're going to get to the other end of the band. Then again, when you go to the edges, the number of different states with the same energy will be reduced. So overall, you have high density of states somewhere toward the middle of the band, and then toward the edges, you're going to have low density of states. So this is the general behavior. But obviously, in solids, oftentimes you're going to have different bands overlapping. So the total density of states is just the density of states for these individual bands, and you sum them up. So this is the end of the review.